thing about analyzing the data without doing any computer processing is that you don't really need to worry about, the software. So believe it or not, what we've done for this surface wave and what we've done for that P wave is we've basically done um, we've done a two-dimensional Fourier transform in some sense. We've actually measured values that we would measure if we Fourier transform the axis this way, and Fourier transform the axis that way. So there's a lot of cool things you can do by eye, and one of my pet peeves about the industry is that they start doing things like this right away. They'll basically take a computer program and basically transform that data that we saw mathematically into frequency along this axis and phase velocity along this axis. So this curve right here that we did by eye, there's a computer program that actually mathematically transforms the data from the space of offset versus time to phase velocity versus frequency. So we kind of know what they're doing when they do that, right? What are they doing? To get phase velocity, we just have to measure, we have to pick a slope and measure the energy along that slope for all the times, right? So this slope is a phase velocity, right? If we can measure the energy at that slope, we can compare it to the energy at this slope. There's no energy at this slope, right? You don't see anything. Is there any energy at this slope? No. There's no energy at that slope. So we basically measure the energy at every slope in here. We'll basically get the energy at every phase velocity. Now, if we then also take that slope and measure the frequency associated with that slope, then we'll get phase velocity versus frequency. And that's essentially how the program works. It's a two-dimensional transform, but you can do it by eye, roughly. So, very much like this curve, what do I see? Well, I guess they got a little bit different. Let's see, 33 we had 400. That's about right. Pretty good, huh? And at 22, we got about 600. Okay, now I was lucky, I knew the answer, so I was able to get the curve in between. But why does this make sense? Why does it make sense that as frequency goes lower, the velocity, the phase velocity? Again, the wavelengths are longer, the wave is seen deeper into the earth, the velocity increases with depth, and that's the kind of curve that we see. Now, if velocity were to decrease with depth, then we might have a different picture. Maybe it'll look like this, going the other direction. Now notice from here, we still haven't developed an Earth model. All we know is the dispersion. So we have a gut feeling right now that velocity increases with depth, just because of our gut understanding of how surface waves work. But we really don't know what the velocity model that generated this is. But we can make some guesses. Let's make some guesses on the dispersion. What would you say that the velocity at the surface is from this dispersion? Pardon? What's the shear wave velocity at the surface? The shear wave velocity at the surface is where this thing dies out. Right? Roughly about this time. Okay? That's the highest frequency that we can see, which corresponds to the shallowest depth. Maybe it's not exactly at the surface, maybe it's a meter or a few meters underneath it. What would be the wavelength right here? We've got a frequency of 55 hertz and a velocity of 250 meters per second. What would the wavelength be? 250 meters per second, this wave, this part of the wave, is traveling in the first 2.5 meters of the surface. So what this says, and I'm just thinking out loud now, is that for the first 2.5 meters, the velocity, the shear wave velocity is probably a little less than 250 meters per second. Got an answer, at least an initial. Now, let's go down to this point right here. At 20 hertz, the frequency is 700 meters. So at 20 hertz, if I take 700 over 20, I get a wavelength of about 35, right? 35 meters. So half of that wavelength is roughly the depth of investigation, which is going to be about 17.5 meters. So this frequency, 20 hertz, goes down 17.5 meters. And I can probably go a little lower, but it's hard to tell the velocity in this part. You notice it looks like, if this amplitude is an indication of velocity, it looks like I could pick a velocity as low as 500 or 600 or as high as 1500 down at the low frequencies. I can't tell what the velocity is. So reliably speaking, I can only estimate the velocity so I've got a subsurface model, and I know that ds is about 250 meters per second down to 2.5 meters. And I know that I can only go down to about 17.5 reliably. And I know that the average, some kind of average velocity down there is going to be about 700 meters per second. So the wave is going to travel in that whole zone, which probably means, by the way, that the velocity is higher than 700 meters down here. 250 up here, if we kind of average this thing, it's probably more than 750 down there. So let's go on and look at what the actual Earth looks like. This is the model that they came up with. Okay? They actually said, oh, it's faster right up at the surface. It inverts to below this. I'm not sure if I believe that. I think you might be able to take 250 and just average the whole thing down to 5 meters, or 2.5 meters, I'm sorry, something like that. But in any event, this is the Earth model that the computer generates. Notice the maximum depth of investigation. Roughly about half of the smallest wavelength that we can measure. And the interesting thing, though, is that the velocities are quite a bit lower down here than I would have expected. And I'm not sure why that is, why that would create a phase velocity, unless somehow something's wrong. I've got to look into that. Okay, now if we wanted to do this measurement and generate a velocity profile in 2 dimensions, we would have to make a survey at different points. And then what we would do is basically do exactly what we did in the past at each of these points. So we basically generate a 1-dimensional shear velocity profile at each of these points and then splice them together into a 2-dimensional picture of the shear velocity as a function of position. So that's how we could image shear velocity. Pretty straightforward. Again, you don't really need to necessarily go through a lot of these machinations to get the very near surface. You can actually do this, at least some of it, from the records themselves. So what we just did, without really introducing any programming, is we basically showed you how you can take records and you can estimate the depth of penetration and the dispersion curve, and then at least for the nearest, the near surface, you can estimate the nearest, the shallowest velocity of your shear waves. go into more detail about this on Friday, how we actually generate the dispersion curves and model this. Actually going from this to this is, again,